Thanks. My name is Xiaoshan, and now a postdoc at Caltech. And hearing all these nice talks and super interesting findings, I'm really excited to share some of these recent thoughts we've been thinking about for those rising time in tidal disruption event. So I guess so far, I can assume we click our user term and conditions that we all agree on that TDEs are interesting transient, great place to study the black hole, the stellar disruption, and the accretion process. So, but they're also pretty complicated systems. This is a simulation snapshot from almost 10 years ago, and it actually provides a pretty nice schematic of showing what are the different components in these systems. So this is a clicker. So we got the disrupted star, we got some debris unbound, escaping from the black hole, some debris are bound to the black hole and kind of falling into it from this little accretion flow near it. Well, each of this dynamic process is important from the initial stellar disruption to the final accretion process, the sort of more or less determining how this event might appear to us. We are particularly interested in these very last few stage of how to actually dissipate the energy and trigger the accretion, and sort of like the classic question of how would you bring all this gas with fairly high eccentricity and down to this accretion flow with relatively low eccentricity. So I do want to highlight that this is the process we think radiation is important. So first, the radiation pressure could modify the gas dynamics. So when we have fairly strong radiation flux and fairly large opacity, occasionally we can get a pretty strong radiation force, and sometimes it could even exceed the gravity pull from the black hole, and these are the systems, we call them super-Addington systems. So people are thinking the accretion process here, as already pointed out, in TDEs could potentially be super-Addington, and we're also seeing that even before the accretion starts, there might be various radiation-mediated shock. And at the same time, these gas are also cooled radiatively, so capturing the transition from optical thick to optical thin region sort of determines what your photosphere might look like, and further giving us some information about how they might appear to us. And some motivations about this work. So we're curious about what could be the pre-peak emission in this event, especially in the optical band, but we're also curious about can we get even more multi-band emission in this rising time. And the other question is how can we get in that reprocessing layer we've been keeping talking about for the optical event. And the next question, we're thinking about, oh, this is a fun one, because if we look at the photosphere evolution in a lot of optical events, we sort of see the photosphere could expand it fairly quickly by order of magnitude within just a few tens of days in the rising time, and then they would start to decay at a much lower rate. So this might suggest that something in the dynamics happens that pop up the photosphere very quickly, and then the photosphere was slowly shrinking over a much longer time. So we're curious about what sort of dynamic process could drive such photosphere evolution. And just in general, I think TDEs are interesting systems to understand sort of the accretion process because we have some hope to sort of trace them from the beginning to the later stage. In a lot of classic super-Addington accretion simulations, we would start the evolution by like a hot torus, but here we got this debris stream sort of naturally giving us a nice initial condition for accretion to happen. So the particular process I've been thinking about is the so-called stream-stream collision, and this happens when we're introducing relativistic precision into this debris orbit. So looking at the schematic plot, if we have a Newtonian orbit, here is an example of an elliptical orbit. If we're introducing the absolute precision, now the orbit will be shifted by some amount when passing the pericenter and leading to this stream self-intersection, or the so-called stream-stream collision, stream collision shock. And if we use a set of parameters that are more relevant for TDEs, here I'm showing a 10 to the 7 solar mass black hole disrupting a solar type star. this would be how the orbit might look like. So these two streams gonna meet each other about 40 gravitational radii. So since they're probably gonna run into each other so close to the black hole, they're probably having an encounter velocity about few percentage of speed of light. So we're thinking that's a huge reservoir for kinetic energy. Even if a small fraction of that getting out and eventually getting observed, that could be an interesting luminosity. So that's some of the initial thought about why we're thinking the string-string collision could give us some pre-peak emission. And we're also thinking maybe during the collision, they could drive some sort of gas outflow and making up the reprocessing layer for the optical event. So let's put everything in motion. Here on the left, I'm going to show a movie for gas density looking face down. So we are looking at the orbital plane, and we're not actually capturing the stellar disruption process. That would happen much further away from the black hole. But instead, we model the debris stream as this thin, cold stream that injected pretty close to the black hole at a fixed fallback rate. So if we play the movie, as the stream-stream collision happens, it launches a lot of gas outflow. Later, the stream sort of disrupted by reform and leading to another round of stream-stream collision. So by the time we're running the simulation, which is fairly short compared to that total 100 days of duration for TDEs, it seems to having these repeating interactions. And the nice thing about doing radiation transfer on the fly is we can look at the radiation energy density together with these gas density snapshots. So here on the right, I'm showing a movie for radiation energy density in lab frame. And this part is getting handled by the radiation transfer module in Athena++, which what we can see here is every time the stream-stream collision happens, it really creates a hotspot on the radiation energy density map. So we got a local enhancement of radiation energy density. Sometimes in between the collision, we also see a column of emitting gas kind of on the other side of the collision. So looking at this movie and these variabilities, because these emissions are probably related to these episodical interactions, we're thinking, can we actually see these variabilities if the system is optical thin enough, or if we are at the wavebands that can look so deep close to the black hole. But before talking about that part, let's look at another example. So this is a very similar run, and the only difference is I dropped the black hole mass by a little bit. So when we drop the black hole mass while keep all the other orbital parameters, we would usually move the collision point away from the black hole. So by the time they collide, they will probably have lower velocity. The available kinetic energy to dissipate might be lower. So generally, we expect slightly weaker interactions. So in this one, for this moment, is sort of the two streams just touching each other. We also see this local enhancement of radiation energy density. But as we play the movie, in this one, they never show a super clear sign of repeating interaction. But instead, we start to have some level of gas circularization near this black hole, and the overall gas density near the black hole start to increase, and so does the radiation energy density. So I think I speed it up a little bit towards the end of the simulation. And at this time, if we look at where is the brightest part on this radiation energy density map, it already shifted from where the string-string collision happens to the central region where gas start to accumulate and circularize. So these two definitely have very different dynamics. One of them had this repeating interaction and sort of episodical emission source. One of them has gas accumulation and maybe an increasing emission source. So the question there is, do they look different? So one other thing we can do is look at what's the luminosity we can collect at a sphere of a fairly large radius that we think outside of the photosphere, and then we can plot it as a function of time. So the first thing we notice, in both cases, we can get a pretty prompt instant luminosity from the string-string collision that reaching something about a few times 44 ergs per second. So I think that's definitely an interesting amount for pre-peak emissions. The rising time here is super short compared to what you might compare to a realistic optical light curve. And that's the part getting constrained by our simulation setup by injecting stream with a fixed rate. But technically, it's not super hard to insert a time-dependent fallback rate, and that's the sort of thing I'm trying to working on right now. but the energetics here should be the reliable part from the simulation. And the next thing we're seeing is these two doesn't look that different. So blue is the one has repeating interaction, while orange is the one has gas accumulation. So we can sort of see some wiggles and bumps in the blue, but they didn't give you an order of magnitude variation. So this might suggest that the photon diffusion is slow, and the time it takes photons to going through this optical thick surrounding region is longer than what the cadence of this repeating interaction happens. And this has been sort of consistent with the fact that in optical we usually see this pretty smooth and nice light curves. That's a lot of variability or interaction happening at the smaller scale could be smeared out as the photon diffuse through the optical thick gas. And given this luminosity, the question we can ask is what is powering this luminosity? So one quick check we can do what's the accretion rate in this system that we can measure at ISCO. So here I'm plotting the accretion rate that calibrates to the Eddington rate, and in the blue we see a very tiny accretion rate that's almost like below 1 Eddington. And in orange we started with a fairly low accretion rate, but eventually start to increase. But in both cases, we're feeding this system with 10 Eddington, and we only get something below 5 Eddington. So we might start to think about where all these mass goes. Are they getting accumulated in your simulation domain, or are they escaping the simulation domain in terms of outflow? So the other thing we measured is the outflow rate in the simulation, and immediately we see in both cases we got pretty prominent outflow. So in this blue one, where we are in the limit of very strong collisions, the majority of gas has ejected in terms of outflow in this simulation. So we wouldn't have much of gas remaining near the black hole for accretion to happen. So that's probably one of the reasons why we're getting so low accretion rate. And similarly, in the orange case, we're seeing the outflow rate is high to start with, and only when the outflow rate drops, we start to have increasing accretion rate. So I guess intuitive picture we're seeing here is this outflow that launched during stream-stream collision. They're not only just giving you a reprocessing layer, they could just delay the circularization or accretion by simply disperse gas to a larger radius. And in some sense, it doesn't matter this outflow are bound or unbound. So even if they are bound, they could still be on the orbit with fairly high eccentricity, and we're not returning to the black hole on a timescale of tens to hundreds of days. So we also have one more round with even lower black hole mass. So in this time, the collision is generally a little bit weaker. It's like a scaled down version for this orange case. We got lower outflow rate to start with and higher accretion rate, and also increase a little bit earlier. In terms of these luminosities we get, they are all sub-Eddington given to the black hole mass. So I guess another a little bit surprising finding that I would say about 2 days ago is it's pretty hard to getting a super Eddington luminosity, even if we're already feeding the fallback rate with 10 Eddington. And going to the question of what is powering this emission, I think we're reaching a conclusion that agreeing with some recent studies that these are mostly different shocks powering the pre-peak emission in the case we see. So on the left, I'm showing the gas density looking face on and side view. So the side view, 0 would be the orbital plane. So we're looking at a slice of the system. And here on the right is just showing the radiation energy density. So in this case, we have very strong stream-stream collision. We think the majority of emission are coming from stream-stream collision. And this outflow, they will also interact with each other. For example, they actually gain enough kick that will not directly fall into the black hole, but sort of wrap around and meet each other at the orbital plane again on this plot. And that makes that column of emitting gas sometimes we see in between the collisions. And it also makes this shells of a preprocessing layer. It's not technically a pressure-supported envelope, but it gives us a relatively uniform photosphere geometry. But in the right-hand case, where we have this more disky structure, we start to see majority of emission are coming from different circularization shocks. One of good example is when this high eccentricity and high density stream running into this circularizing gas, we can almost see a shock forms where the radiation energy density getting enhanced. And what's curious is we also get a pair of tiny spiral shock at the center of the black hole. It's sort of getting truncated by the high density stream at the pericenter and didn't propagate super far away, but that's one of important angular momentum transfer mechanism in our simulations because we don't have magnetic field over here. Well, yeah, we can talk about this. So another thing we try to do is to estimate the photosphere property in these simulations, but getting the photosphere property is pretty challenging. We did the most straightforward things by integrating a long line of sight that radially towards the black hole, and we can calculate what's average size and the temperature at this radius where the integrated optical depth hits 1. So in terms of the size, in all of the case, the stringent collision can quickly pop up the photosphere to something like 10 to the 14 centimeter. And in terms of the gas temperature, we got fairly high temperature to start with. That's just after the collision happened, the outflow haven't propagated that far, that we're looking at this pretty hot post-shocked gas. And when the outflow propagate outward and push the photosphere outward, we start to get in this much cooler temperature down to something like a few times 4K. And this would telling us average evolution. Looking at the distribution is also interesting. So here again, I'm showing gas density and radiation temperature, which is pretty close to gas temperature in most of the regions because they're pretty thermalized. And this green line is tracing where we think the photosphere would be by doing the radio integration. And in this case, if we look at the photosphere temperature, they're relatively uniform. So at all the different places, we're getting something like a few times 10 to the 4K. But in these two cases, we got more discrete structure. I think we are seeing some levels of the viewing angle effect the model we're proposing, that there are some regions that's pretty optical thick, and we can probably getting a lower photosphere temperature and larger photosphere size. But in these polar regions where we don't get much of the gas, maybe we're getting a smaller photosphere size and a higher photosphere temperature. One of the important difference is here we haven't formed a proper superaddentate disk. We're including a hot corona. Here it's just generally more optical thin because we don't have much of the gas over there. I guess maybe a little bit different picture here is through these optical thin channels, photons are probably easier to be getting advected out if you have some hot photons generated at smaller radius. Instead of like Adrian disk, you have the hot electron corona to upscatter all your photons. And so I'll jump to the takeaway slides, but I think there might be some interesting to show regarding to the discussion we had in today and yesterday. So one of the events makes me excited in the radio detection that we can trace back to the outflow launching. That's actually the pre-peak. So I'm trying to comparing with, can we get in proof of concept to check that this outflow launched during stream-stream collision can more or less giving us some similar signals. But this launching radius of 10 to the 16 centimeter is way beyond where the simulation domain is. So what we did is just randomly picked some of this unbound outflow and reading what's their current velocity and position, and then we can use this as initial condition and integrate their ballistic trajectory. So this is like assuming they don't experience very strong further dissipation. By doing that, we can get in some of the properties to say they can propagate something like 10 to 16 centimeter, and by the time they reach in that distance, which takes usually about 2 to 3 months, you can get in a velocity about near like 0.1 c. And there are also some bulk quantities we can look at what's the total unbound mass produced in this simulation and what's the kinetic energy carried by this unbound outflow rate. And if we're doing these comparisons, surprisingly, we can actually select a set of parameters that seems to be more preferred in terms of total kinetic energy in this unbound outflow. We got something that more close to the lower energy limit. In terms of mass, we got a very low outflow rate, but that could depend on various parameters. In terms of velocity, we got something that more close to 0.1 c. It's pretty hard to get beyond that velocity, but this is only the double check for one of the simulations. So I guess if we eventually being able to do this for more parameters, that might be interesting. But so far, it's pretty promising that at least maybe some unbound outflow during the stream-stream collision, if we have strong collision, can give some early radio emissions. I guess I'll just stop here, maybe? Is that okay? Yeah. Yeah, and I'll see.
Hi, thank you. Extremely interesting. Have you quantified the mass in the outflow as a function of the black hole mass? And can you go back to the, you had a plot with the outflow fraction on the upper panel. Yeah, this one. So do I read it correctly that the outflow strength decreases with black hole mass?
Yeah, that's just because we're fixing all the other orbital parameters. So that's the case when we're increasing black hole mass, we would move the collision closer to the black hole. Right. So we get very strong collision, and it's easier to unbind gas if you have very strong collision. Of course, there are other orbital parameters that can affecting where the stream-stream collision happens, like penetration factor or your stellar mass and radius. So I guess by changing the black hole mass, we're really just trying to cranking up and down where the collision is happening.
So you would expect that the outflow mass keep decreasing given the setup as you decrease the mass to 10 to the 6, for instance? Or
if we're still using the same orbital parameter, I guess that would probably be the case.
Do you remember how much mass is in the outflow?
You mean like absolute number?
Oh, yeah, or percentage of the star mass.
I haven't think about it in terms of star mass, but I remember it's something like 10 to the minus 4 solar mass for the unbound gas, if I remember that correctly.
Okay, thank you.
Yeah, thanks.
Great talk. I had a very similar question, so it's a good slide to be on. Have you tried plotting how the outflow fraction or accretion fraction scales with like the kinetic energy of the shocks? Because that would kind of be taken into account, or yeah, then you could scale the other properties like mass and flow. Yeah, everything.
That's a really good point. That would be something I would wish to do, because if we think the emission, if we think the emission is coming from the stream-stream collision, then it should more related to kinetic energy instead of accretion. Is that sort of the motivation if we look at the luminosity outflow mass as a fraction of kinetic energy?
Yeah, I was also thinking if there was some nice relation, then you could just people could just input things like what the m dot, what the collision radius, and then therefore the velocity would be, and then scale your simulation results potentially, which could be really nice.
Yeah, that would definitely be interesting.
Can you just comment on the resolution of your simulation, especially at the northern shock? In terms of the cell size over the stream size, for example?
So that's also like a question people has been discussing for so long, and it's so challenging. So the question is asking about the resolution and how the resolution affecting the nozzle shock. I was reading some literature recently. There are theoretical calculations that suggesting the stream could be compressed to very thin, especially perpendicular to the orbital plane when passing the pericenter. And in the most cases, it could be compressed to like hundreds or tens of times to its original stellar radius. That would make it almost impossible to resolve in these global simulations. I think it's probably interesting to show our really trying to do a resolution study in this radiation hydroruns. So from left to right, we're looking at increasing resolution, and I'm putting the pericenter resolution here for reference. In the case of radiation runs, it's a little strange that when we have very low resolution, we got a very thin returning stream. And as you're increasing resolution, you start to getting slightly expanded returning stream. And then as you're increasing resolution, you start to getting a little bit thinner width again. And this is the cut through the vertical plane at the pericenter. So these are just like the cross-section of the stream. So in this lowest resolution case, we can see the stream already collapsed into one cell. And in terms of radiation energy, it's a lot of radiation energy compared to other rounds. So this is one of the scale in the radiation rounds that we should resolve is the optical depth of the stream. So in this case, we're not resolving the optical depth of the stream. So all the energy is deposited in this couple of cells, and also before the stream reaching the pericenter, it becomes too optical thin. So we got a lot of energy leakage over here. In these cases, we think we're still not resolving all the numerical dissipation, but we start to get in the right optical depth. At least you have the stream vertical structures, and then you can compare if they're optical thick or not. So I guess this is the best we can do for now, and see if there's more flexible refinement scheme we can use.
Thank you for the details.
It's probably too detailed.
Very nice talk. So I would like to understand more about these simulations. Like you say, when you have a lower black hole mass, the accretion happens further away, but eventually you'll have more materials accumulated near the center. So what is dissipating the energy? I mean, when the shock is weaker?
So one of the impression we get is when you have lower black hole mass, it's easier to accumulate a little bit of gas near the black hole. So the collision point will be further away from the black hole. There will be some gas with slightly lower angular momentum, probably already falling near the black hole before the collision happens. And for some reason, the collision themselves is also weaker, so wouldn't get all the gas into the outflow. You will have some gas accumulating near the simulation domain. And comparing the dissipation efficiency from stream collision shock and circularization shock, we think circularization is much more efficient in terms of damping energy or eccentricity in this gas. So once you have a little bit circularization, it's easier to bring more gas to circular orbit. So I guess that's probably one of the reasons when you have weaker stream collision, just a little bit weaker, it's easier to get in more gas circularization.
Okay, so by circularization shock, I think you mean you have some gas, I mean, kind of accretion flow structure, bond flow structure, and then the stream continues to interact with that.
Yeah, that's one of them. And this stream, these gas are not on perfect circular orbit, so they could have a little friction and also a little interaction too.
Okay, thanks.
I actually have a quick question. So if I look at like the top 4 plots there, it seems like one of the big effects that is occurring is kind of the spreading of the stream in the transverse direction. So have you looked at, so like I guess what that effectively is doing is kind of reducing the density of that income or outgoing stream into the incoming one.
Yeah.
So have you looked at like trying to determine or quantify how big of an effect that is by doing just like a test case where you just take the streams themselves and just let them go into each other without doing the actual circular or the the wraparound?
Oh, just looking at the interaction themselves. Oh, that would be interesting. I haven't think about that. Okay. Yeah, but it's definitely doable. And that'd maybe do some local study near the pericenter.
Exactly,
That would be doable.
Sorry. Yeah, so I have a question about regarding your, you have a luminosity and temperature, the 2 panel. It looks like the temperature is slightly too close to 10 to the 5 Kelvin than what observations show there. Yeah, exactly.
This one?
Yeah, observations are closer to 10 to the 4 Kelvin.
Yeah.
So it's slightly too hot.
Yeah, it's slightly too hot.
Yeah.
But this is also like average of all different slides of sight.
The luminosity seems to be fine, but it's slightly too hot. But and then the consequence is that in the optical band, it's slightly too dim compared to, let's say, Assassin-14 Li or some of these optically detected ones. So is it possible that there is some additional opacity in the gas that you can raise your thermalization radius slightly larger by a factor of 2, and then you're good? So,
that would be possible.
I know. What kind of opacity did you use?
I'm using the opal opacity, which shares the same physics as the MESA underlying. So it has bound and bound free, but this is a great calculation. So we assume all the photons have same energy. If there's any effect that can alter the photosphere radius, that might be interesting to do, like say a multi-group round. Then you can look at for different photon energy, they should have different thermalization radius.
That's right. Yeah, opal would be based on the Rosalind mean. The Rosalind mean is not the good one for thermalization. And that's the details. The Rosalind mean tells you the radiation flux, the total flux. So that's right. So the luminosity is right. But the color would depend on the actual frequency-dependent opacity in detail instead of the Rosalind mean. So if there's a chance that you can get higher opacity, that would work. Yeah.
Yeah, that would be interesting. Yeah.
So I'm interested in the multiple collision scenario you had, and you said it could lead to episodic emission. On what timescales would you see this, and is this what we're seeing here, or is it?
So the time scale of repeating interaction should roughly just be the free fall time near the accretion radius, which in this case is fairly short, like a couple hours.
Okay.
So I guess that's one of the cases we are in the limit of very strong interaction. I've seen one other simulation where seeing repeating interactions, which is a spinning black hole case, but also a close encounter in some sense. I guess maybe at some stage they actually happen, but I'm not sure you can observe this effect because this bolometric-ish gray light curve we measure are much more flat than what I might think about from this emission. So because of the reprocessing, because of photon diffusion.
Okay, thanks.
All right, one more question.
Yeah. So I was interested in your radio flare, like AT 2020 VWL slides that you were showing toward the end.
It's a bold comparison we did.
Yeah, so I guess this one is kind of an interesting one because then of course it had the second rebrightening in radio. I don't think it's on this plot, but so this is one of the TDEs where we see it rising again the second time in the radio. So I'm just wondering, I guess, about the time scales in your model, because I think the energy and the density are kind of in what we're seeing for these late time outflows. But I'm wondering if you could comment more about the timescales and how you could change that or things like that.
Yeah, so the timescale in our simulation will be unfortunately be a tiny slit on this plot.
Exactly.
So it's only like 10 days.
Limited.
And that's already like a pretty expensive calculation. So that's why we have to do the ballistic extrapolation, which might not be accurate. So in order to, I think all these late time behaviors are super interesting. In some sense, they are a separate question for early time, how you form the accretion disk, to later time, how the accretion disk evolve. I would so much like to do some studies on these late time disk evolutions, but I think this one is pretty hard to say anything happening at the scale of like 1,000 days, 100 days.
Well, hopefully in the future then.
Thank you.
All right, let's thank Xiaoshan again. And meet back here in half an hour.